Hello everyone, I'm Francesco Romano, Developer Relations Engineer for Android at Google, and today I'm going to share some best practices in building apps that are optimized for a variety of different devices. I know all of you are able to build great apps for Android phones, but look around. We have phones that unfold into tablets, we have tablets that dock with the keyboards and mice like laptops. We have support for external displays. Android is powering TVs, cars, XR headsets, and users are interacting with their apps using styluses, keyboards, D-pads, and so on. This is to say that the interaction model on Android has grown far beyond single touch on a small screen. How do you build apps for this new world? Well, you still want to start by focusing on the core quality of your app. It should be stable, performing well, be accessible, and follow the best design patterns. But if you want to grow your user base beyond phones, you simply cannot stop there. The next pillar of a good app is to be adaptive. And by adaptive, I mean an app that is not restricting its orientation and aspect ratio, but it's resizable. It offers optimized layouts for different window sizes, doesn't lose the state, can be used with the mouse and keyboard, and supports interactions with other windows, like drag and drop. Now, this step is extremely important, and we have found that developers who have already optimized their apps for larger screens were able to port them to other form factors like cars or XR headsets with almost no additional development. Also, starting from Target SDK 36, most of the orientation, aspect ratio, and resizability restrictions will be ignored when on devices with a display bigger than 600dp. So, an adaptive app, it's the most important and necessary step to reach users on different form factors. And an adaptive app already provides great experience across form factors. But if you want to optimize even further, you can still create even better user experiences by leveraging the unique qualities of each form factor. For example, you can optimize your app for the different postures of a foldable device. You can add support for spatial panels in XR headsets. You can deliver a truly desktop experience by supporting external monitors, multiple instances, and advanced keyboard shortcuts. So, if all of that makes sense, stay with me. The next 30 minutes we're going to explore how to implement adaptive apps with a focus on desktop windowing in particular. I choose desktop windowing as a primary example as it's one of the most extreme environments for your apps. Users can resize your apps from tiny windows to huge canvas, and they can move your app to external displays with different densities, different characteristics, and also they primarily interact with your app without touch. So it's a very different interaction model compared to phones. Let's start with the best practices for adaptive apps. So yesterday my colleague Roberto gave a talk on adapting apps for multiple screens. If you missed it, go back in time or watch the recording. That talk was focused on the UI and the layouts of the app, while I'm going to focus more on the functional aspects of building for different form factors. Cool. There are three main aspects that you should consider to make your app fully adaptive. First, provide optimized layouts for different window sizes and preserve the state across configuration changes. You don't want your users to lose their workflow if they simply resize the window. Then you should also adapt your navigation strategy for better ergonomics. On larger surfaces, the navigation should stay on the side. On smaller areas, it should be at the bottom of the window. And last, provide at least some basic support for mouse and keyboard. The foundation to build adaptive layouts consists in using the window size classes as inputs for your layout decisions, because they give you the essential context about the available space. Also, do not reinvent the wheel. Leverage the supporting Jetpack libraries for test and optimize adaptive components, and get inspired by the canonical layouts to build the perfect experience for your specific use case. We have a bunch of updates at the link here, but I want to quickly highlight just some of them. First, this week, Jetpack Window Manager gets its stable release for version 1.5 and includes an update to the window size classes. It includes the new large and extra large breakpoints to help you design layouts for desktop devices and ultra-wide monitors, which is very important now that Android supports connected displays. And they are very easy to use. Basically, the usage is the same as the previous version, but you just need to use the breakpoints version 2 instead of version 1. And then you just apply the correct layout when you are sure that your app has at least that much space. If you're using the Material 3 adaptive library, the new breakpoints are already included, starting from version 1.2. You only need to opt in by declaring that you want to use the new breakpoints. Otherwise, it will still use just the compact, medium, and expanded window size classes. Okay, now let's head to the core part of the talk and see how to build desktop-level Android apps. For those of you that are not familiar with desktop windowing, this is a relatively new feature that allows users to run multiple apps on screen at the same time. It's available directly on tablets, on certain tablets, while on most phones and foldables, it's only available when attaching an external display. And it comes with a new system UI to make users more productive and a new set of APIs to allow developers building enhanced experiences. A few minutes ago, I was saying that this feature brings resizability to the extreme, because your app can live in a window of almost any size and aspect ratio. Even if the tablet has a bigger display, that doesn't mean that the app will live in a bigger window. Actually, the minimum window size is 386 by 352 dp, which is smaller than most phones. So this fundamentally changes the way we need to think about UI. Users aren't just making small adjustments when resizing. They can expand your app to fill a huge canvas. So your UI should not just stretch, but it should adapt. See, for example, now in Android. This app reflows intelligently, revealing more panels, providing a draggable divider for maximum flexibility, using different navigation components. And this is all very important. But beside the UI, can you offer more powerful feature in this environment? One example is allowing multiple instances of your app. Because a great desktop experience is more than just looking good at any site. It's about the workflow and the productivity. Let's say your app can edit documents. You really want your users to be able to open 2 documents at the same time on different windows, so they can reference one while editing the others, or maybe they want to share content between the windows with the drag and drop. And in Android, there are essentially 3 ways to start an additional instance of your app. Either from a UI affordance, from your own app, from the system UI, but also with the drag and drop gesture, And now we're going to see how to implement all of them. First of all, in order to support multiple instances, you need to define a launch mode for your activity that supports multiple instances. In this case, I picked a single instance per task. That means that this activity can only run as the root activity of the task, the first activity that created that task, and therefore there can only be one instance of this activity per task. Remember that a new task in desktop windowing will always result in a new window. So, if that activity supports multiple instances, you can start it by adding those flags in the intent. If you use just the new task flag alone, the behavior is this. If a task is already running for the activity that you're starting, then the new activity will not be started. Instead, the current task will simply be brought to the front of the screen with the state it was last in. But if this flag is paired with the flag activity multiple task, then it will skip the search for a matching task and unconditionally start a new task, which is required if you always want to open a separate window. And the exact user experience will depend on, of course, on your custom UI. For example, Chrome provides the entry point from its contextual menu. So you click Menu, New Window, and it will start another instance. Next, it's starting another instance from the system UI. Okay, you can add this property in your manifest to tell the system launcher that your activity supports multiple instances. So users may be able to start another instance directly from the launcher, from the taskbar, or from other system UI components. One example is the new window menu that pops up from the top up handle, which is shown only if that property is set for the current activity. And that gives users a hint that your app supports multiple instances. This is already great, but there is an even more natural way to start another instance. And look at how Chrome starts a new instance by dragging a tab out of the app window. We can implement that by leveraging the drag and drop API from the Compose Foundation library. The important part are the two flags to customize the drag and drop behavior. Drag flag global same application indicates that the drag operation can cross the window boundaries. Drag flag start intent center on unhandled drag tells the system that if the drop event happens outside of any visible window, it should be delegated to the system itself. You may be asking, okay, but how does the system know which activity to start? We are providing the information in this function. Let's have a deeper look. So the clip data that usually contains the data you're sharing through drag and drop needs to contain the intent sender of the activity that you want to launch. When the drop event ends outside of any visible window, the system will capture this intent and start the activity. If you want to look at an open source app that implements multiple instances, check out the Kahir note-taking app on GitHub. This is an interesting example because we not only implemented the start of a new activity on another window, but also updated the navigation so that the new activity will directly open the selected node. Because otherwise, by default, it will just open another home screen. Okay. Going back to Chrome, I want to check if you were paying close attention and noticed something interesting about the Chrome UI, something different. Chrome is using a custom app header bar. So we already saw how all the apps in desktop windowing have this header, which is reported as a caption bar type of inset. And It's an inset, so it's important to account for this when drawing the content edge to edge, but you can do more. See, Chrome is optimizing the use of space by drawing the tabs directly in the header bar. Otherwise, by default, there will be a lot of unused space. And to do that, apps can use this new appearance type to make the header bar transparent to allow custom content inside the header bar. If an app uses this API, the system automatically hides the app's name from the bar to leave more space for the custom content. Let's see a sample. Okay, look, we are rendering the content only if the caption bar is visible. Now, this is a core principle that we are not checking if the device is in desktop windowing, if it's a tablet, if the display is big enough. No, we are just checking if the feature that we need is there. And this is what adaptive means, removing the assumptions regarding the device type, but just checking at runtime what is available for the users and then use it. Going back to the code, if there is a caption bar, we draw a row that has the same dimensions of the header bar. We set its background, and then we add our tabs within it. We also need to avoid overlapping with the system components, like the app logo and the window controls on the side. And we use padding for that to calculate the right safe padding. You need to measure the caption bar and then subtracting the areas reserved for the system components. You can learn more about how to calculate it at the link here. Good. Now, some visibility considerations. It's easy to check if a component is visible or not when your app is the only one using the whole screen on a phone. But what about desktop windowing? So I want to explore this topic using your favorite app, Androidify. Yes, Androidify does run on desktop windowing, and it's actually optimized for that. So let's take a moment to visualize this little but very interesting optimization. Androidify provides this video tutorial in its home screen. On small windows, you can reach the tutorial by scrolling to the right, while on bigger windows, it's always visible. The optimization here is that Androidify pauses the video playback when it's not visible. How? Compose 1.9 introduced this new modifier called onVisibilityChanged that registers a callback to monitor whether the node is inside of the viewport of the window or not. In this case, we want to trigger the callback if the node is fully visible for at least 500 milliseconds. This is just a time buffer to avoid the callback being called if, for example, you are scrolling back and forth too fast. So we can store the result of the callback in a mutable state and then use that to power a launched effect that will play or pause the video according to the visibility. Cool. But that is not enough. There is another situation in which the video could not be visible to the user, beside resizing. Even if the layout is fully expanded, there is a situation in which the video is not visible. Can you guess? It's when another app occludes the video player. So in this case, the video player is still within the viewport, but it's not visible to the user. And by default, the onVisibilityChanged modifier doesn't take into account Z-order obstruction of composables nor window occlusion. So in Androidify, we use another strategy to handle the video playback in this case. Let's see how. So starting from API 35, Android introduced this function to register a presentation listener that receives a callback when some conditions on the occlusion state are met. You can register it when it's attached to the window, and of course unregister it when it's detached to make sure you're avoiding any possible memory leak. And then you need to use this trust presentation threshold object to define the conditions to trigger the callback. In this case, the threshold is to have 25% of the window rendered, or you can say more than 75% of the window occluded, for more than 500 milliseconds. Again, time buffer to avoid triggering the callback if another window is just quickly being moved over the video player. So you store the result of the callback in a mutable state, and now we have the information. But the thing is, the information is in the activity top level, because remember we had to override the unattached to window function. But then we need this information in the composable that hosts the video player, which is way down in the hierarchy. You can pass this information down over I don't know how many composable. On Android 5 we used composition local, which allows you to create a 3-scoped named objects that can be used as an implicit way to have the data flow through the UI tree. It basically means that all the composable here under main navigation will be able to access the occlusion value. That allows us to modify the keys of the launched effect so it gets restarted when at least one of the two condition changes. So now we can pause the video if it's either invisible or if it's occluded by another window. Okay, we are heading to the end of the talk, and I want to take a moment to share best practices around handling external displays. There are two different modes of how Android devices react to external displays. When the phone is connected to a display, the phone state remains unchanged, and a blank desktop session starts on the external monitor. The device and the display act as almost two individual systems where apps are specific to each display, and this is the experience that you have, for example, on Pixel 8, 9, 10, if you are on the latest beta. When a desktop windowing enabled device, like a tablet, is connected to an external monitor, the desktop session is extended across both displays. Then they function as one continuous system, allowing windows, content, and the cursor to move freely between the two displays. And this is the experience that you have, for example, on the latest Samsung S11. Best practices to ensure high quality user experiences in this new environment. Okay, first, do not assume that the display object will remain constant. But when a user connects or disconnects the external monitor, or even moves your app between displays, the underlying display object that is associated with your app's context or window can change. And its properties like the size, resolution, refresh rate, density can all be different. If you have hard-coded values based on the phone screen, for example, this will break the layouts on the external display. Closely related to the first point, you must account for density configuration changes. So external displays can have vastly different pixel densities. You need to make sure your app responds correctly to these density changes. That means using density-independent pixels for the layouts, providing density-specific resources, and ensuring that your UI scales appropriately. And then finally, think beyond just the screen. Because when users connect to an external display, they often create a more desktop-like environment that involves frequently using keyboards, mice, trackpads, webcams, microphones, and speakers. So ensure that your app works seamlessly with these peripherals, handle the keyboard shortcuts, the mouse pointer interactions, and correctly support the external peripherals, audio output routing, and so on. Okay. In this talk, we have seen different apps handling different aspects of a good adaptive app. We have seen now in Android with its multi-pane, draggable layout. We have seen Kair and Chrome handling multiple instances. And of course, we have seen Androidify with its adaptive layout and its occlusion detection mechanism. Okay, you may be asking, but can I see an app that with a single code base is running across phones, tablets, desktop, cars, TVs, and XR headsets? Of course, the answer is yes. We have an open source one. Earlier this year, my team took Jetstream, which is an open source app initially designed for TV, and used the new Compose libraries to extend it to basically all the Android form factors. And if you attended Roberto's talk yesterday, you already know that. Otherwise, go check it out, as he explored this process more in details. Okay, few takeaways. Try the desktop windowing experience. See how your app actually behaves in this environment. And think adaptive. You know, resizing, for example, can happen all the time. It can happen in desktop windowing, but also when you unfold a foldable device or when you enter split screen mode. So shift the whole logic to rely on the window sides, not on the display sides. Do not reinvent the wheel. Take advantage of all the Jetpack libraries we have seen that will make your life much easier. And also, try to, don't look at desktop windowing as, oh, this is another feature that I have to support. Instead, try to see how you can make your users happier by leveraging the unique qualities of each form factor and these new interaction models. And as always, try to have fun while doing it. Thank you.